Yes. Well, hello everyone and good morning and welcome to this today's webinar. So we are going to discuss about analyzing model performance using TensorFlow Profiler. The reason we are discussing this or the reason for this topic is that previously when I was talking about Keras tuner, so there were few specific questions as to what is the overhead for all these Python operations or what is the overhead for all these operations that happen and how you can reduce these operation time or let's say dataset loading time specifically so that your model trains faster, you utilize your GPU more better and you get far better results in quite a less amount of time if you have a resource constraint, a specific resource constraint, like an individual whenever he's training his own model on his own laptop, maybe he has around 2 GB or 4 GB of memory, which will take more time even for a simple data set like MNest. Okay, so we are going to see how we are going to improve model performance, what are those steps, and how TensorBoard and TensorFlow Profiler is going to help us in our tasks. So to begin with this session, I'm going to start sharing my screen. Okay. Yeah. So I hope my screen is visible. So this is a few words about me, what I've done so far, what I've been doing, and so I have mentored around 800 students and 50 plus
Ashwin, you
faculty.
need to add your presentation screen in the stream.
Okay, okay. Just a moment. Okay, no? Yes.
Yeah.
So, yeah. So this is a bit about me on how I've been helping students, on how I've been helping the community become part of the AI deep learning community. So moving ahead, yeah, so let's begin with what is TensorFlow. So TensorFlow is basically was developed by Google Brain team and released in 2015. TensorFlow has many versions like TensorFlow Lite, TensorFlow JS, and NVIDIA's version as TensorRT. These have different use cases or different purposes for to be specific. TensorFlow, as we are already aware, TensorFlow Lite is used for light or on edge devices like Jetson Nano, or let's say even Raspberry Pi with a Google Coral USB accelerator. Whereas TensorFlow JS is quite a web-friendly framework for all those web developers and everything. And TensorRT is an inference engine to improve inference time on various NVIDIA devices, like just I mentioned, Jetson Nano or TX2 or many such others. So the TensorFlow name comes from the word tensor, which are basically multidimensional arrays, and TensorFlow uses data flow graphs. So if you are aware about the language called VHDL, you would know how data flow graphs work, or basically how sequential execution of instructions work. So what all you can do using TensorFlow is pre-processing, building models, and evaluating, testing, and deploying. TensorFlow has a very good framework or a specific part called TensorFlow Extended, where they have made it quite easy to deploy your models using some Docker containers and all that stuff. So yeah, these are the advantages in a brief introduction to TensorFlow. So what's a tensor? A tensor is a vector matrix of n dimensions. So there are the tensors of four ranks: rank 0, rank 1, rank 2, and rank 3. So these are basically scalars, vectors, 2D matrices, and so on. So this is how you define a tensor. We'll see how we define a tensor. The reason to tell about these is we are going to optimize these operations. So it is better to know how these operations work or how these operations are managed. And graph, so all tensor operations are conducted inside a graph. If you've been coding in TensorFlow, or if you've been using TensorFlow, you would have seen you have to initialize a specific session where you initialize the graph of the model and then you perform your operations, and each operation that gets performed is called an op node, or let's say an operation node, which are connected to each other and which perform their own task. So these tasks or these computations are performed together using a tensor which has a node and an edge. A node is something that carries some mathematical operations. Okay, let's say you have to multiply two matrices, or divide something, or take square root of a matrix. So this node is what it carries, and the edge carries the input output relationship between nodes, like what's the input to the node, what's the output to the node, and all that stuff. So this was quite an overview of TensorFlow. Moving ahead, so just now we discussed how do you define a tensor. So this is how you define a specific tensor. This is a tf dot, so to write it, tf dot constant, and you define your tensor values. So this is a matrix 1 2 3 4, and this is another matrix. So to add these or multiply these or do a matrix multiplication, so you can use these kind of functions, and this is how you define a specific tensor, or how you initialize a tensor, or more specific way to define this is how you initialize a tensor. So also to note is that you can have tf dot constant, but you have to remember one thing, that you cannot change these values. So if you want to have your matrices or your scalar or vector to change, you can use tf dot variable, and you can initialize that tf dot variable with a specific range. Let's say start is 1 and end is, let's say, 10. So you can change these values according to your needs, so you don't have to rely specifically on the constant value. Moving ahead, so why profile? Why do you need to profile your model? So we've already built our models, we've developed our models, we've defined our layers, and let's say we have four convolutional layers, four dense, one or two dense layers, dropout layers, and all that. But why do you need to profile? Because while training your models, or while having multiple models for your deep learning application, performance is the key for all the solutions. We've seen a lot of times that people complain about performance being slow, or in the model training time, or in the inference time, specifically model training time, because there are a lot of data set taken away situations. So that is a far more important aspect as to increasing the model training time. So faster model training times lead to faster iterations and reduced overhead. Okay, so what does this mean is that, so if your model is training faster, if your gpu is being utilized, or if your cpu is being utilized, so you should make sure that your cpu and gpu are both working in sync, and they are not losing any time, or they are not idle for a specific time. Okay, so I guess Suyok will take questions a little bit later after this session. Okay. Yeah. Thank you, Aditya. We'll take these questions after this session. Yeah. So, uh, your CPU and GPU, when you have these two specific devices, remember while we are in this session, what if I call it a host? It's a CPU, and a device is a GPU. So when we'll see a Jupyter notebook on how to do all these things, whenever I say host, it's a CPU, and a device, it's a GPU. Okay. So whenever GPU's tasks are what your neural network is defined to, and CPU's tasks are, let's say, getting those data sets, preparing those data sets to send to GPU. So while this is happening, some or the other, either host or the device, shouldn't be idle for too long time. Otherwise, it will take a lot of time for you to train, even for a smaller data set. But the more important part is, it is always not clear, or always not clearly specified as what needs to be optimized. Okay, so if I say I have a data set of, let's say, ImageNet data set, and I have this data set with my own data set, and it ranges around, like, let's say, 1 GB or something. So to pull 1 GB data from the IO using IO operations and passing them to the GPU, the overhead to do these operations, which is called as an input pipeline. So the overhead to do these operations, or to also consider Python overhead. So Python, as we all know, is an interpreted language. So the Python overhead is also there. Also the overhead for calling various TensorFlow APIs. So it is always not clear as to what part should be optimized. And this is where TensorFlow Profiler comes into picture. It exactly tells you what are the specific pain points in the model that you're trying to train. And it helps you analyze where the most time was spent, where the most memory was utilized, how to evaluate, or how to look into the specific operations and how to improve your model. We are going to see how this is done using TensorBoard in a once we finish this. Okay, so TensorFlow Profiler. As we discussed, TensorFlow Profiler, it provides you a set of tools so that you can measure your training performance. And if you've been through the TensorFlow Dev Summit of 2020, there are a few developers who were talking about TensorFlow also mentioned that they are using internally this tool too. So this is not something that was just released out in the open in open source, but they have been using this tool internally, and once they found this sufficient, they have released this tool, and it's quite a useful tool for let's say a performance engineer's life cycle point of view. But if you're a one man team, or if you're the person in your group or in your company who does everything, this tool is going to save you a lot of time. Okay, and the new version, the recent version of TensorFlow is well integrated into TensorBoard, so you don't again have to go through ton of logs, because whenever you're training your model, let's say you have a Keras callback setup for each on epoch end, or let's say for each iteration for each operation, then you have a quite a bit of longer log, let's say even in MBs, and then it becomes a tedious task to scroll through all those unnecessary messages and see what exactly is happening inside your model and how you can improve it. So instead, you can use TensorFlow Profiler using TensorBoard, and it gives you a graphical overview of how your model is working. Okay, or where do you need to make those specific changes, and how to, most important part is how to reduce your training time and how to make your resources use more efficiently. Moving ahead, how do you start on profiling? So as I mentioned, it's a simple Keras callback. You import TensorFlow, you create your model over here. I hope it is visible in all those black background. So you create your model here, you define your model here using TensorFlow.keras.sequential. Maybe, as I said, you have convolutional layers, dropout layers, and all those layers fixed. And then you define a Keras callback. I hope everyone is aware about what Keras callbacks are. So we are going to specify a TensorBoard Keras callbacks. You can also use these callbacks for other different purposes. And so here you're going to define a TensorBoard for Keras callback, wherein there are two things that you're going to specifically mention. One is logdir, wherein you're going to store all these logs that TensorBoard will in turn import while we are going to see what metrics are there. And profile batch. Now, profile batch is something of uh, to understand that which profile batches or which batches do you want to profile, which specific batches of this training do you want to profile. So after you've defined this callback, you just call model.fit, you pass those training images, labels, you define some epochs, how many epochs you want, you mention your validation data, and you define a callback. Now, one more important thing to note here is that these callbacks, if you see, will also have their own. If you think it in that way, these callbacks will also have their own execution overhead. But according to TensorFlow, these callbacks don't have that much overhead over all the other operations that are being performed using model.fit. So these overheads are not going to quite uh, hamper your model performance. If, let's say, if I'm going to profile every batch, every other batch, and if you think that what if my CPU is being utilized also for the profiler and for all these model training tasks, then there's quite a bit of overhead for that. So, but no, TensorFlow has specified that these callbacks don't have that much of an overhead while calling model.fit. So, moving ahead. So, what you get in TensorFlow Profiler. So, there are these four common tools that you can see: an overview page, an input pipeline analyzer, and TensorFlow stats and GPU kernel stats. So overview page is something that will provide you a top level overview of model performance and recommendations, like a step time graph. It will tell you how much time the compiler spent using fetching inputs, giving outputs, or let's say kernel loading, host loading, and all these times are specified in this overview page. In the input pipeline analyzer, what you see is models data input pipeline bottlenecks. Now, what are these input pipeline bottlenecks? So, these bottlenecks are specifically designed, or these not designed, these bottlenecks are specifically encountered while you're reading your data, while you're doing some pre-processing, which is mostly optional some of the times, but while you're doing some pre-processing, these input pipeline analyzer will give you an idea of how much time is spent reading your files, how much time is spent pre-processing your files. A simple example for pre-processing would be an OpenCV call to, let's say, morph or move your data, or let's say flip your images. So these can be some pre-processing steps. And the third part is file transfer from host to device. Again, remember, when I'm saying host is CPU, device is the GPU. So input pipeline is this entire pipeline from reading the data to processing the data and transferring this pre-processed data to the device. Now, all these things are happening on the host. So your CPU is going to be quite busy while all these things are happening, and you need to understand, and one needs to understand that this is the place where most time is spent fetching data and pre-processing data and transferring data. This is where exactly the most number of time is spent, and this is happening all inside your CPU on multiple cores. Okay, so we need to make sure that we reduce these times and reduce these bottlenecks and improve our inference time. So this is what will be told in the input pipeline analyzer part. TensorFlow stats is nothing but it will display a statistics about all the different TensorFlow operations that you're executing, and let's say an input out, or your optimizer operations, or your session calls. So all these calls and TensorFlow operations are being displayed in the TensorFlow stats. And GPU kernel stats is nothing but it displays the performance statistics of GPU. So how much GPU was utilized, how much memory was utilized, and all those things. Now, the specific reason to mention these four tools is that these four tools are common for CPU, GPU, and TPU. Okay, so you can use this tensor board or TensorFlow or Keras callbacks using TensorFlow profiler to profile CPU, GPU, TPU using all these four tasks or all these four pages. These are called pages. Yeah. So this is how a typical profiler looks like, or as we've seen the introduction about how these various pages are. So as you can see here, there is performance summary telling you average step time. So average step time includes all these times. Okay. So this is how it works. So as you can see here, there is also a step time graph. Now step time graph consists of compilation time or output time, input time, time to kernel launch, host compute, device to device, and device compute. So, and if you go below, you can see what are the recommendations for next step. Don't worry, we are going to see these all these operations and this TensorFlow TensorBoard profile live in a Jupyter notebook. So you just need to understand what all these mean, and then you can see as a specified here your run environment, so you can understand how many the GPUs or how many hosts have been used, how many devices have been used, and all those things. So here's this part specifically is what we are going to focus on, which is a recommendation. This TensorBoard callbacks utilize your model training and all those model operations, and then they have a small recommendation or some steps for you to determine where you're spending most of your time and what you can improve. As you can see here, this is not an input bound program, as this is an optimized tensor board of an optimized network. Okay, so you can see here what next tools you can use, and let's say TensorFlow stats or a trace viewer. So these are some recommendations. Moving ahead, this is how typical TensorFlow stats page look like. So if it's not visible clearly now, it's okay. We'll see this in Jupyter Notebook too. But to give you an overview, TensorFlow stats is basically an overview of what is happening inside all those TensorFlow operations. How many TensorFlow operations and for how much time were they uh, executed on the host or on the device while the device or while the model was being profiled. Okay, so these are different TensorFlow operations, and these are the different statistics on how much time was spent doing all those typical profiling operations. So these operations will also include a specific table over here as shown below, wherein you will have the number of occurrences, how many time specific operation TensorFlow operation occurred. Let's say let's take a TensorFlow operation of fetch data or get next data. So how many time did get next data operation got executed during a specific model training time. Now here total time, you can see total average time, all self, time on host, time on device, and all those things. So this gives you a proper idea of what TensorFlow operations are taking more time and where do you need to save your time on host and on device too. So this is a very combined approach. Now, moving ahead, how do these changes in performance or how do these tensor board keras callbacks or all these recommendations help you? As you can see here, so this is a Deebler GAN CNN used, and so these are all these methods that you can use to improve your model performance. So initially what the author did was he used just basic tf.data calls, and these tf.data calls gave him let's say around 1014 seconds for 5 epochs for a specific data set using Deebler GAN and using float 32 operations. So one thing here to understand is what are these float 32 and float 16 operations. So these 32 and 16 are the precision bits that your weights are going to be initialized or that your weights are going to get updated. And so you have to also understand that using 32 precision bits will obviously make your precision or obviously make your model more accurate, and it will also have less time to compute or do all those it will also take more time to do all these computations because these are 32 bits that we are talking about. And one method is also to use float 16 if your application is not that let's say accuracy specific, or you can manage some accuracy, you can manage having 90% accuracy instead of let's say 94 or 92% accuracy you for speed. So you have to have a certain trade off. You can either have speed or you can either have accuracy when dealing with 32-bit or 16-bit operations. Then you can go ahead with 16. So initially this took around 1014 seconds for 32-bit and 1021 seconds for 16-bit operation. If they move ahead with parallel calls, now these parallel calls are, let's say, while you're normalizing your data or while you're doing some pre-processing operations, you can have these operations in parallel calls, one in executing parallelly, so that you shed your overhead of executing all these instructions one after the other. Then what happens if you cache the data? Now let's say I have cached all those data, or the author has cached all those data using Deebler GAN or using tf.cache. So the execution time or the training time was significantly reduced from 1014 to 615 seconds for 5 epoch, just because the data set was cached. And for float 16, obviously we see a little less time if you're doing some prefetching. Now the difference between cache and prefetching is that once you're caching the data, you're storing the data in the runtime memory or the memory that is being currently utilized, and that's it. You're just making the data readily available. Whereas in prefetching, what you do is, let's say a TensorFlow operation is happening in time t. Okay, so if a specific TensorFlow operation is time t, this prefetch calls or this specific prefetch call will import, or let's say get the data that is required for the t plus 1th call beforehand, while the teeth call is already being executed, so that after the teeth call is being executed, all the data that is being required for your t plus 1th time is already available with the CPU or GPU. and this saves a lot of time from handing over data from CPU, GPU, and doing disk IO operations constantly. Then these are XLA. XLA is a compiler that TensorFlow uses, so these also improve your training time. Now using two GPUs, obviously this will have a good impact. And then two GPUs plus strategy, some strategy that the author might have used, but two GPUs always have a advantage. But if you have one GPU, you can always use these three operations, which are num parallel calls. You can cache your data and you can prefetch your data. Okay, so this is how the improvement that you see overall using various TensorFlow operations. Now let's move on to the notebook. The node, okay, yeah. So, okay. I hope this is visible to everyone, and you can read those specific codes too, so that you don't spend time zooming into your screens or like fetching where it is. So let's start with profiling. How we do this is we first import obviously our necessary packages, then make sure to have the latest TensorFlow version and the latest TensorBoard version. While this tutorial was written on the TensorFlow documentation, it was around 2.2. So make sure you have the most recent TensorFlow and TensorBoard version, and this is how you install your TensorBoard plugin profile for profiling. Now we've checked here whether we have the recent TensorFlow version or not. Let me also run this simultaneously, so that when we are doing some improvements, we already have the previous data. Okay, so the TensorFlow version currently we are using is 2.3. Now we are going to test whether TensorFlow has access to the GPU or not. These are simple steps that you might have encountered. Now we are going to train our model using a simple MNIST dataset to classify images. I'm sure everyone is aware about what an MNIST dataset is. So, and one more most important part is these common datasets are now available in TensorFlow datasets. You just need to install TensorFlow datasets, and all these common datasets are readily available. So you don't have the overhead of downloading these, separating them into train and test and all that. So this is readily available. Now you split your data set into train and test. There are some other arguments to like shuffle files as supervised and with info. You can have these or you cannot, like you can skip these. It doesn't matter. These are not quite important. You have to. The most important part is splitting the data set between training set and the test set. Okay, now we are going to pre-process our data. Now this, what does this pre-processing means is that what I said earlier, pre-processing is like normalizing your data sets or some other operations if you're familiar with OpenCV pre-processing and all that. So what we are doing here is we are normalizing our data sets, our images in our data sets. A reason to normalize is that you have pixel values ranging from 0 to 255 for around MNIST data sets are around, let's say, I suppose 60,000 training images and around 10 or 20,000 test images. So each image will have a pixel value from 0 to 255. Now having your filter run through all these numbers from 0 to 255 and multiplying your filter with each pixel or each 4 by 4 patch of pixels is going to consume a lot of resources and a lot of computation. So instead what we do is we normalize all those images so that we have a value between 0 to 1, which is far easier and far faster to compute. Now, as we discussed earlier, we are going to map normalized images over here. Now, you can obviously check this map operation in the TensorFlow documentation. And so we are going to map these operations to normalize image. Basically, it's simple as calling the normalize image function. Okay. Then moving ahead, we are going to train with a batch size of 128. After, I hope you've executed this part, and then we are going to also map our we are also going to normalize our test images and get a batch size of 128. Now we have created a simple image classification model. I've just included the notebook just has 3 layers because this is just a demo sort of a notebook and you don't want your model to be running for quite a longer time just for viewing it. So we have three layers over here. One is flatten. So we are passing 28 by 28 by 1. So this 28 by 28 is the image size, and one is the color scale. So these are grayscale images, and we have two dense layers over here. So first dense layer contains 128 neurons, where we have used ReLU as an activation function, and the last dense layer, which is obviously the classification layer, has 10 neurons, or let's say unit 10. This is because we have 10 different classes in MNIST data set. So we are going to have predictions for 10 different classes, and activation function is the softmax function. As we have 10 different classes, we are going to use categorical cross entropy and Adam optimizer with 0.001 as learning rate. And the metrics that we are focusing is the accuracy. So accuracy is an important part for our model. Okay, so moving ahead now, this is where we are going to discuss our TensorFlow or TensorFlow profiler. So as you can see here, we have initialized logs, so where we'll store these logs that TensorBoard will use to import and show us some statistics. So we are storing these logs in a log folder, and we are using a tboard callback as I've shown you earlier. Using log dir, you pass the logs directory. Histogram frequency, we'll see later what it is, and profile batch, which batches you're going to profile. So here in case 500 to 520. Now you obviously call the model.fit function. Now this model.fit function will train for two epochs using the validation data and giving these callbacks. Just a moment. Hmm. This is correct. So just a bit of overhead over here. So we'll rerun this. So while we are rerunning this, we'll see what TensorBoard or TensorFlow chaos callbacks have already had for us. Okay, so I had pre-run this beforehand for us to understand how TensorBoard Keras callbacks work and how each of the operations are performed. So let me just zoom out a little bit so that you have a proper overview of it. So if you see here, this red part is where most of the time of your CPU or your host or device was spent. So as you can see, this red part is attached with the input part. So dealing with inputs was where the most time of your host or your device was spent. So we obviously need to reduce this specific input time so that we don't waste so much of time just processing inputs. Okay, so this is what we are going to focus on today. And moving below, so we obviously have got the recommendations that our program is highly input bound, because 82.8% of total step time is waiting for input. So out of all these execution time, 82.8% of total step time was just waiting for inputs. So fetching the data or pre-processing the data and all that. And obviously we need to reduce this time, because 82.8% is a lot of time just spent on the data set itself. Also, we have here a statistic: 6.1% of total step time was sampled on kernel launch. This is still okay, because you're going to require different number of kernels, and different number of kernels are going to be initialized. But if you still want to improve this, you can have some other methods that we're going to see later to improve this. Now, this 7.1% of total step time is sampled on all others time, which were not profiled, which we did not profile using this TensorFlow profiler, which may be Python execution overheads or other Pythonic operations. Okay, So moving ahead, here is what we've discussed earlier in the previous slide of the difference between 32-bit operations and 16-bit operations. As we were doing all the operations in 32-bit, so all our 100% device compute time was spent doing 32-bit operations. But in order to improve performance, if we use 16-bit operations, then it will obviously improve the speed of training, but you will have some hampering on the accuracy of the model. Coming back, you have here is a performance summary of what all was happening, and it all took 27.7 milliseconds for all this to happen. Device to device, device compute time, host and kernel launch, how much time did it take to launch the kernel, input time. See, as you can also see here, 22.9 milliseconds were itself spent on fetching and processing inputs. Okay, so that's a quite a lot of time. So this is what an overview page will give you. Now, moving ahead, we have an input pipeline analyzer. As we've seen what time we are spending on what specific resources. So we have an input pipeline analyzer for that. We obviously have a lot of logs, as I already mentioned, that you would have to otherwise fetch a number of logs for this. So you have a lot of logs, and then okay, so meanwhile this is loading, we'll check. Okay, so our model was trained successfully. I guess it was some issue with our specific runtime, and that's why we had a error. It shouldn't normally take that much time, but let's wait. So as we've discussed earlier, input pipeline analyzer is something that will tell you more about how input pipeline was defined, how it worked, and what all other steps or what all other TensorFlow operations were used, so that you can later understand and optimize that. A bit of snag here on TensorBoard. Okay, so while this is loading, I hope, yeah. So as visible, our accuracy is quite decent, 89 on first iteration, and let's say 95 on second iteration, with our validation accuracy also quite high. So we've done quite a decent job. Okay, so we have our tensor board initialized over here, and this is how you go to the profile section, and it will load the profile for whatever operations that were executed. So again, so now we have here again the time was spent in the input part. So let's see where the most time was spent. Okay, so this is a more brief idea of where the most time was spent. If you go on each of these nodes, you will find the duration on which step took how much time for what particular operation. So this is also quite helpful to understand where you need to improve. Now going here, if you see this entire green area and if you see the description, it says that 99.47 host side time was spent for data pre-processing itself. Okay, so this is quite a lot of time spent just to pre-process data. So what you can do here to improve or to reduce this time is you can either have num parallel calls using dataset map. You can check dataset map in the TensorFlow documentation because it's quite a vast topic. Otherwise, you can use prefetch or interleave, or you can use cache to reduce this time. As we already discussed what prefetching or caching means, so you can use this. We'll see how we are going to cache or prefetch the data. Okay, so this is what the input pipeline analyzer tells us. Now if we go below, we can see kernel stats. These kernel stats are nothing but how much time, how much total duration each kernel was executed. So I guess we all are familiar with Adam, applying Adam. So around 14.1% of time was spent for applying Adam kernel, and all these times are likewise. Now these are the GPU kernels that were executed on the GPU. Okay, so these kernels that we are seeing here, optimizing or matrix multiplication, calculation, adding bias, updating weights. So all these were happening on the GPU, and you can see a number of occurrences of how many times it occurred and what operation was it. So this is what you see in the kernel stats page. Now in the memory profile page, what you see here is how much memory was allocated and how much memory was deallocated, if or whether your data was fragmented during these operations, and the memory breakdown of, let's say, different operations. So this is what memory profile gives you. TensorFlow stats is something wherein you'll get all the operations done by TensorFlow on host and on device. A specific thing to look at is here. It mentions that 92.9% time was spent on the data set, which was obviously on the host, because host deals with the data set, whereas the device deals with all your model training and all that. So 92.9, which is quite a lot of time, was spent on the data set. Now, coming to the most important part that we're going to discuss today is the trace weaver. Now this trace weaver will tell you how these different operations were sampled across a specific time frame. Okay, so you'll understand where which operation, for how much time, and for how much total time, how many operations got executed. So, and here is where we'll understand what CPU or GPU is doing while one of the other is performing operations. So while we are waiting for loading, so this is an overview of trace weaver. You'll understand what different operations were performed, what different time it took. Okay, so just to give you an overview, as I already said, host is the CPU and device is the GPU. So let's zoom into it a little bit, and let's focus on one specific function called as data iterator get next. Okay, so what this function does is, let's check how much time we spent using. So we spent around 21.8984 milliseconds on fetching data on every iteration. So this is the time that this operation TF data iterator get next spent to fetch the data, to process to or to send it to the GPU for every operation. Okay, so for every training or for every not, we should not call that an image, but for every TensorFlow operation, training operation, 21.984 milliseconds were spent to fetch the data. And if you see here clearly, your GPU is just sitting idle in this time. Okay, so you're not utilizing your GPU properly because you're letting your GPU idle around for 21.984 milliseconds, which is quite a large overhead when it comes to training on very larger data sets of hundreds of GBs. Okay, so you're letting your GPU sit idle for quite a while just because your CPU is fetching the data set and cannot send beforehand. Okay, so this is the time we are going to focus. So how do you improve this? How do you make your GPU or CPU work simultaneously? Not exactly simultaneously, but how you reduce your GPU idle time, and how do you reduce the time required for your data set to fetch and start processing? So for that, what we are going to do is, we are going to again define our training and test data set. We are going to load our data set. Here what we are going to do is, here we are going to cache and prefetch our data. Okay, so this caching and prefetching, as we already discussed, so caching means it is readily available in the runtime memory, or let's say in the temporary memory, and prefetching is getting the data that is required for t plus one call while the teeth call is executing. So when the teeth call is already, when the teeth function call is already, when it finishes executing, it already has the data for t plus one call, and it does not go back on fetching the data set. So we are again going to normalize our data, and we are going to do the same caching and prefetching for our test data set. Now let's run model.fit over here, and let's train it on for two epochs, and after that we'll see how much difference did caching and prefetching make for performing our operations. So again, the accuracy has far bit increased, 97, 96, and 97. So let's load our tensor board again and check whether did we have any improvement while caching and prefetching or not. So this is how you're going to use TensorFlow Profiler. Obviously, we are focusing on one or two pages, but you can go ahead and check all the other pages which are very important in understanding how TensorFlow operations are being executed, where the most number of time is spent. Okay, so as you can see here, our average step time has drastically reduced to only 3 milliseconds. Okay, so if we go a little bit up and we check our previous time, okay, so this will load the time for this current iteration. Okay, so if we had checked our previous time, it was something around 29.2 milliseconds. So we have drastically reduced our time, our performance has drastically improved just by caching and prefetching data. So what recommendations we are getting is our program is moderately input bound, still 7.4% is spent, which opposed to the 81% or something. And so we have quite bit improved on our time. And so yeah, so again we are using these 32-bit tensor operations, we are not using 62-bit as of now. But now let's get to our trace viewer and see how much time actually did we spent on prefetching or getting the data. The TensorFlow.get iterator next operation that we saw earlier, which was using around 21 milliseconds, we'll get to know how much time now after caching and prefetching the TensorFlow get iterator next is spending. Okay, so again host is CPU, device is GPU. Okay, so let's zoom into it. So this is the iterator get next do compute. Let's see how much time we used. Okay, so if you can see here, we just spent 49.43 microseconds fetching our data set or making it ready for our GPU, as opposed to 21 milliseconds or something, 21.984 milliseconds, which we were doing previously. So this is quite a lot of improvement, and this is quite a less amount of time our GPU is being idle. One may think that okay, the GPU is still sitting idle over here, but no, it's not that case. GPU is idle for a quite lesser amount of time, in microseconds, 49.43, that too, as opposed to the 21 milliseconds that were being spent just for getting the next data. And if you go below here, you can see all these operation times were also reduced. So this is how TensorFlow Profiler or Tensor board using TensorFlow Profiler will help you in analyzing your models, will help you in understanding how different operations or how different iterations are being used in the TensorFlow graph, and how you can improve these operations, how you can utilize your CPU and GPU well. So this is how you do that. So I guess this marks the end of our today's session. So I will make sure that these notebooks and these example and all these slides are available on my GitHub. And if you are interested in learning more on computer vision and deep learning, machine learning, and everything, you can scan these specific QR codes, which will take you to some awesome lists on GitHub that you can later check on. And these are the references that I used, I found useful. These references you will too find useful. So So I guess you can go to this, specifically the deep learning book by Goodfellow. It is an excellent book to learn deep learning and all specific mathematics and everything about deep learning. So yeah, so thank you so much for being a part of this session. And yeah, so these are my details. If you would like to contact me at any point of time regarding anything related to TensorFlow, deep learning, or anything, as usual, you can follow these links and you can always email me if you have any questions. So, thank you so much. I guess I hand it over to Sujay. Suyog, sorry, Suyog.
Thanks, Ashwin, for hosting today's talk. It was
Yeah,
really helpful. Uh, I hope participants had enjoyed this,
yeah,
and look forward for your more sessions with the developers community.
yes,
So this
sure.
session is going to be available for playback on YouTube on the same link. So maybe afterwards, if you want to share your presentations, like you can just put it on the comments on the, or you can put it on our GitHub page. Okay.
Sure, sure. I guess there
Okay.
was a question too or something.
Yeah, there was only one question from Aditya. How to easily load 1 lakh rows of data in TensorFlow? I guess this is pretty basic question and should be available on the community,
Yes.
community, right?
Correct,
Yeah.
correct. Just to tell him that, so how, no matter how many rows are there, you can still use load CSV data method using pandas and everything, and it's readily available. So there's no specific thing as loading easily or anything for your data. Okay. Yes. Thank
Ashwin
you.
and participant, I also want to add in one more thing here. I don't know whether you guys are aware Redis AI. So Redis AI is the module, right? Why I'm sharing this because as concerned to today's topic,
Yeah.
I work for Redis Labs and we also have Redis AI is the module which is available in the community as well, community version, right? So this
Uh,
library is allowing you to host Redis database with AI capabilities. So internally, it has TensorFlow, PyTorch, and other libraries as a models. And as it is, Redis is a in-memory database. You can actually train data and keep it into rich data structures, like for example, hash or some other data structure that you want to use, so that your real-time processing can be much faster. And this model is also supporting on basically different resources like CPU, TPU, GPU, so that you can actually think about having real-time processing.
okay.
So I would suggest try this, give a shot, and we have seen certain benchmark compared to other basically frameworks or tools. So this
Uh,
basically two benefits, right? One is performance, and second thing is it is already bundled with TensorFlow,
yeah.
PyTorch, and other
Correct.
libraries. You don't need
Correct.
to worry about how I should deploy this and how I should learn Python because ultimately
Correct.
you're going to Redis APIs, right? So you can see
Okay.
this Redis.io site where you have certain examples, and there are a lot of examples that we are working where there is a lot of real-time
Wonderful.
process. Example, capturing the stream from the video, live video, and then you say that whether that is security threat is or not, like something like that. So there are a lot of things are quite easily manageable. Yes.
Okay, wonderful. It supports TensorFlow, so that's very good. TensorFlow,
Yeah.
PyTorch too, and Onyx runtime, because Onyx is like is slowly becoming a standard for making or creating models on various different frameworks. So it's really great. I guess we should check this out too. Sure.
Thanks, Ashwin. Have
Thank
a
you.
great weekend,
Thank you.
guys. Yeah.
Yes, yes. Have a great weekend. Thank you, everyone.